Okay. Excuse me, did somebody just call 911? I didn't hear. What's the problem? Should I need to turn the lights up, or should I wait for your eyes to become homostatically adjusted?
Homostatically adjusted.
Okay. All right. Everybody good now, or do we need the lights up? Because it is kind of dark. Okay. Going once, going twice. Okay. All right. So we're going to give my series of lectures now, and I'm going to be sort of leading you in on some of the statistics stuff. So the first assignment you had and done, and its first assignment, of course, was really rough and tough and hard to do, wasn't it? Yeah, that's what I thought. Okay. The second assignment, I had thanks for Zach for pointing out the fact that I meant to send you some data and I hadn't. You now have the last piece of data that you need for that. It'll come as, if you haven't looked at it yet, it comes as a spreadsheet. Oh, jeez, I'm gonna turn it down. There we go. Show me. No, it's okay. I'll turn the lights up a little bit.
I'm the only blind man in the room.
No, there's another one up front, but he doesn't. I don't have to see anything. So,
You already know this stuff.
yeah. Anyway, so when you open the spreadsheet and see all those lines, the data, remember just the data under your name is what you're doing. I didn't have time to send each cut and paste and send all to you. So everybody's got different data. So if you compare your answers to somebody else and wonder why they don't match, duh. Okay. All right. So the first two tests are probably the most commonly used tests in statistical analysis by and far, because they deal with the one question that gets asked more than any other. Is the average of these numbers different than the average of these numbers? So is the length of the fish differ significantly between these two things? Or is the weight, the mass of these deer different? All these different things is a very common test. So, quick review before we start. Okay, name some measures of variability.
Wait.
Name some measures of variability. If I'm measuring the variability, that's a unit, which is fine. I'm measuring the variability of a sample or population of data. How would I report that? Measures of variability.
Not mean, median, and mode, but
Range.
Range is one.
Standard deviation.
Standard deviation.
Variance.
Variance. There we go. We got variance, standard deviation, and range. Of which range we don't want. That's no good. Standard deviation. That's nice, but it's only good for reporting data. It has no other value in your world. And then you got this variance thing, which thing is like weird. It is weird, but it's very, very important. You're going to be using variance a lot. Okay? Now, name some measures of central tendency.
Mean, median, mode.
Maybe it's quite all right. Mean, median, mode. This time they get it. Mean, mode. And we're going to be focusing on mean. Thank goodness, because that's what you've been focusing on all your life. So, okay, so that's what we're going to be talking about today. We'll be using a variance and mean a lot. Okay, here's our case study. So some of you in this case study will look very familiar. To some of you it won't. Okay, I have a team of highly trained aquatic scientists. You may know some of them. This picture's getting a little aged. So this is my highly trained team of scientists here. And this is where we are working at. And what the objective is to quantify and compare the sizes of crawfish populations in these two ponds, Pond A and Pond B. Okay. So, this scientific question. What might be an appropriate scientific question for this study?
Good question.
I hope to heck I'm not stumping you for an answer here.
Do you want an answer?
Oh, I'd like an answer. Yeah.
But is there a difference in size between the two ponds? Is one?
Does crawfish size differ between the ponds? Okay, that's all we're trying to do here. Okay. Okay. What is a good research hypothesis?
Pond A has larger crawfish than Pond B.
But you made a leap of faith there. How might you do that a little bit more conservatively?
One of the ponds.
That's my man. Okay, right there. Okay, yeah. the research hypothesis would be crawfish size difference between these two ponds. That you can do. But if you say it's bigger than A, then I'm going to start looking, what brought you to that hypothesis? You know, and that's where a lot of you had problems in your first paper, that if you said something and you gave me nothing to bring me there, I was saddened. So you've got to explain how you got to that point. So that's why we're going to be very conservative here. Okay, so here's what we do. We throw out these traps. Some of you have done this already. Traps in the water. Leave the traps for a while, come back, they're crawfish. Okay, get the crawfish out of the traps. We take their mass and we take their length. The length is called carapace length, which is the length of the little tip of the nose right to the end of the carapace. Okay. Here are our results. Okay. Pond A got 43 crawfish, Pond B 39. The average length in millimeters on Pond A, 68.6 versus 76.3. Those are the plus or minus standard deviations. The mass, 34 grams versus 38 grams in the ponds. Okay, so we look at those numbers for a minute. Here's them graphed. So again, that's what I would expect to see. Pretty soon you're going to know how to do graph, and so your graphs will come out gorgeous like this all the time. And we look at that, and now we of course ask the question. Sorry, this is length here, and that's mass there. I graph both sets of data. Okay. Do central tendency and variability differ between these two ponds?
Yes.
I hear a yes. Do I hear a no? Good, because they're good. Of course they do. They're different. But is this difference statistically significant? That's wherein lies the rub. Are they significantly different? And so we need, whenever you have that word significant, and I hear people throw around significant all the time, and like I say, well, the difference between these two is significant. And I ask them, how do you know? Well, look at that one, like that one. Yeah, they look different. How do you know it's significant? Because when you say that word significant, what you are saying is I have an applied interpretive statistical analysis with a given alpha value, and I have shown a p-value smaller than that alpha value. If you can't do any of that, then you don't have significance. So what is the test here for this? The test we're talking about now is called the two-sample t-test. This is it, the godfather or godmother, whichever way you want to play, of all the statistical tests. Okay, it is a parametric test. The test for the differences between two means. And by golly gosh, much of your life you're going to be testing the difference between two means. Okay. What is a parametric test? This is a review. Okay. It's a test that has a lot of power. Okay, so by a lot of power, okay, but I always mean we're going to avoid a type 2 error. You know, we're always avoiding a type 1 error, but this is so powerful I'm also avoiding a type 2. That's how good this is. It has a lot of power, but your data must meet certain criteria. If you don't, you can't use the parametric test. And what happens is the statistics police come and arrest you. Okay, so you cannot use, you can only use a parametric test. You only use that power for good. You must have the right reasons. So what are the criteria then? Okay. The observations of one set of data are independent of the other set of data. In other words, if I have a line of data here and a line of data here and I'm going to compare them, if I mixed up this line of data, there's not a problem because they're not connected to that line of data. But if I've got some sort of, if I'm looking at length and weight, or length of, let's say I'm looking at length of left leg versus length of right leg of deer for some reason. Okay, those are paired. They're connected together. I couldn't use a t-test to show that the left leg was longer than the right leg. I couldn't use a two-sample t-test to do that. Okay, so there isn't a specific connection between the data points. The distribution of the observations is discrete. I have single point observations. Nothing is using categorized data. Like these aren't, I have this big group that I throw things in, small, medium, and large. that wouldn't work. Okay. The data are normally distributed. Dr. Coward explained that rather well. And then the last one, and this is one of the bigger ones here, is this is the one we often have to mess with. The variances between the two samples do not differ significantly. Okay, so before I can use this test to check the means, I have to know that the variances aren't significantly different from each other. So that's where the kind of the rub comes in. Okay. So kind of focus on this in a minute. This idea of the variances, how would I know? Sorry. So as I've explained, what is the purpose of the t-test? Someone tell me. The purpose of the t-test is to do what?
Find the difference between two means.
What results? What are you checking to see if each one of these tests I'm about to give you is to check for significant differences in what though? Specifically, the means. So the t-test, you're looking for differences, significant difference between two means. Means, okay? Don't try to keep all these tests in your head. You just don't reach into the bag and grab any old test and use it. You have to know what your purpose. Okay. So the test to determine if there's a significant difference between two variances is not a t-test. It's an f-test. Okay. So I've just snuck in f-test on you here. Okay. So do a quick summary. Okay. Usually what you want to know in the world, the thing we generally want to know is to answer your game management question, your resource management question, your wildlife manager question, is you want to make the statistical comparison between two means. That's usually what you want. That's a two-sample t-test. Okay. But you can't do a two-sample t-test until you know if the variances are or aren't significantly different. So you got to take a step back. Okay. And that's an f-test. With me on that. Okay. So sometime in the future, I don't know, someone said, what is the purpose of an f-test, and left you a blank and a 2-point value on it? Could you be able to answer the question? What is an f-test? What is a t-test? Make sure. Okay, so the f-test. Okay. So again, it is a procedure to establish whether or not the variances, there's the symbol for variance, f squared, are significantly different. So it's a test, so it's going to have a null hypothesis, and it's going to have an alternative hypothesis. I'm testing the variances between two different sets of data. Here are the hypotheses. The null hypothesis is that the variance of one of the sets of data is not significantly different from the variance of the other set of data. But the alternative hypothesis is they are significantly different from each other. So that's summary test right there. Calculating the F statistic is probably one of the easiest things you can calculate in statistics. To calculate the F statistic, all you do, so we know that one population, we can calculate, you already showed me, on your last test, you calculated the variance of a sample. So you calculate the two variances, variance for the sample 1, variance for sample 2. You look at those numbers and you figure out which one is bigger, and you divide it by the smaller. Done. Okay? The larger variance divided by the smaller variance is the F statistic. So it's a real easy number to calculate. And so the bigger the difference between those two, the more likely it's going to be. The bigger that number gets, the more likely it's going to be significant. Okay. So here's an example from our crawfish study. Back to what we're doing here. Okay, I think I'm just going to focus on mass now, okay? So I want to see, I'm asking the question here, do the variances differ significantly between the sample we took from pond A and the sample we took from pond B? Okay.
Sorry, that's what
It said right there, does the variance for mass in pond A differ significantly from the variance of mass in pond B? Okay. Here again are my hypotheses. that the variance in pond A is not significantly different from the variance in pond B. Variance in pond B is significantly different than the variance in pond A. Okay. What are the variances? If I ask you right now, give me the variance of mass for pond A, what would it be?
34.1, 38.2.
No, those would be the means.
9,
What?
9.
No, that would be the standard deviation.
Yes.
Aha, I remember now. It's what?
You square the standard deviation.
Yeah. What is the square of the standard deviation?
81.
81 and 64. Okay? That's why I picked on the mean because they're real easy. Okay? So remember that the variance is equals the square of the standard deviation. So the mean, the variances are 81 and 64. So to calculate what is called my F statistic, my F value, or as I'll be referring to from now on as the calculated F value. Okay. The calculated F value, 81 minus 64 is 1.26, if you trust my math.
You mean divided by, not minus?
Divided by, yes, always divided by, not minus. Divided by, divided. So I should have said before, I thought I said before, I didn't, obviously not. Okay, so the larger divided by the smaller. Are we okay on that now? All right. So there we go. What does that do for you? Not a damn thing, right? Okay. Okay. Turn to page 91 in your hymnals. Got your hymnals with you? Bring their hymnals.
You round that, that's, if you round that up, since it's one,
You don't need
one,
it.
two, I didn't know if it made a difference
It's
or
not
not.
gonna make a difference. Okay.
Can.
So, if you don't have your share with a neighbor, okay, anyway, for those who don't have them with them, page 91 is what is called the table of values used with the F test, or better known as an F table. This is what it looks like. For those that haven't seen it. Okay. Very so you have one. Good. That's the F table. Here you go. Okay. All right. So it's a table with, excuse me, I'm sorry, I stepped right over your stuff. It's a table with columns and rows. Of course, all tables are tables with columns and rows. That doesn't really help us out that much. Okay. So the thing is, we have what we have calculated is called the calculated F value. What you're about to get from this table is called the critical F value. And we're going to compare these two to each other. And how they compare is going to tell us which hypothesis, whether or not we've rejected the null hypothesis. Okay. So, first of all, you have to determine the degrees of freedom for the numerator. Okay. Which of these two values is the numerator? 81. Okay. So what you would do is you go to this table, and basically the columns are the degrees of freedom for the numerator, or the columns are what you do to figure the numerator. And these columns numbers run from 1 all the way up through 10. Then they go 12, 15, 20, 24, 30, 40, 60, 120, infinity. Okay. We're looking for determine the degrees of freedom for the numerator. The numerator is 81 minus 1, so that would be 80. I don't have a column for 80. That doesn't matter. If you don't have a column for the one number you want, you go down to the next smaller one. And on your graph here, on your table here, that is 60. We have a column, we go from 40, 60 to 120. So we know that our critical value is going to be somewhere in this column here. So now we go, see where I am on my slide here. I think I got that worked out. Okay. This determines the correct column of the table. If your degrees of freedom isn't there, go to the next smaller number. That's 40. Okay. I'm wrong. Don't worry about it. Okay. Okay. So the degrees of now you determine the degrees of freedom for the denominator. Okay, so now you run down, you basically, this determines the correct row for the table. So now we're doing the same thing over here, using the number 64. And where they intersect, the number that's there, that is our critical value. So if I run down here one way and run it across the other way, now the number 16. Okay. Cool. What value do you get where those two come together? 1.67. Okay? That's the critical F value. Okay. You remember, before we go on, let me write down what our calculated F value was, before I forget it. I can see myself forget. 1.26. Okay, so let's write that down. That we calculated
Denominator is positive.
calculated F
You take the 64
was
minus
1.26. Critical F, you said was what? 1.67?
Yes, sir.
1.67. Excellent. Okay. Here's where we're at then. We compare the calculated to the critical. If the calculated F is bigger than the critical F, we reject the null hypothesis. Okay? If the calculated F is less than the critical F, we do not reject the null hypothesis. I'm going to ask you two very, very important questions now. First one, what is your conclusion about the crawfish data?
But the one pond does have bigger crawfish.
Just asking about the data.
Do not reject HO.
Okay, so according to this, what it says here is we are not, the thing here is our critical F is bigger than our calculated F. Okay, so our calculated F is less than critical F. We do not reject HO, right? That's important question number one. Even more important question number two, what does this mean? What did we just show? What does this tell us? I'm kind of on purpose get you lost. Because I want you to come back and realize, why in the hell did I do this in the first place? What does this tell you about the two ponds?
Data significant?
The variance is different.
So, you say that the data are significant. I would, first of all, I'd ask you, what data are you talking about?
The F value.
Okay. Are they significantly different? No, they are not significantly different. So if the F value shows no significant difference, what does the F value test? So I'm trying to bring it all back. What were we testing when we first started this thing?
Whether or not they are significant.
What's the they? I'm tired of hearing they.
The variance.
The variances.
The variance.
The variances. That's what we are. This is what happens, and there's no easy way to get around it except to drag you through it bloodily like this. Okay? Don't lose sight of what you're doing. I'm testing the variances. I find the variances are not significantly different. What? Why did you do this test in the first place? Do you remember? Why was it he made us do these tests? One of the criteria for what? For parametric data. So you're saying you're kind of happy you didn't find a significant difference right now. Because this is telling you is, really, I want to know about the means. I don't really care about all this malarkey here. But I've now shown them, I don't have significant difference. I am free and clear to navigate with the t-test. That's what you've done here. So don't lose track of that. So, okay, quick terminology. If you conduct an F-test and you do not reject HO, which is what we just did, okay, there is no significant difference in the variances. These data are considered to be homoscedastic. I'm not teaching you this word just because I think it's a cool word that you have to know. You'll be seeing this word again in your life very soon, like on Excel's assignment number 2. Or 3, yeah, thought number 2. Okay. If you conduct an F test and you reject the null hypothesis, now you know that there is a significant difference in the variances, and your data are heteroscedastic. Okay. If you have homoscedastic data, you're free to use you're cleared for that feature to use the F test. I mean the t-test. If you have heteroscedastic data, you have to use a modified t-test. Okay, great. We took care of that. Now let's go back and go after the data we really wanted. All right, once again, it is used to determine if there is a significant difference between 2 and only 2 means. So here are your hypotheses. So you have, remember again, we always have a null hypothesis and we have an alternative hypothesis. The test is at going after the null hypothesis. We want to show that the odds for the null hypothesis to be true are less than 5% chance. That's what this is all about. Okay. So the null hypothesis is the mean of one sample is not significantly different than the mean of the other sample. Alternative hypothesis is the mean of one sample is significantly different than the mean of the other sample. This is our test. Okay. Again, quick side note about hypotheses, just to keep you on track here. I want to mention this, again, this is kind of a sidetrack, but I want to mention it because it's going to become important a little bit later with stuff we're working about here. When you test, there's 2 types of tests when you're testing hypotheses. You can have a one-tailed test or you can have a two-tailed test. So the hypothesis we set up, mean of 1, not significantly different than the mean of 2. Mean of 1 is significantly different than the mean of 2. This is called a two-tailed test. Okay? I don't care which side you're on, whether one's higher or one's lower than the other. So that's called a two-tailed test. We don't really, it's not telling us anything about the direction of the differences. We're not asking that one is greater than the other. If I said that my hypothesis was that one sample is less than or equal to the other as my null hypothesis versus one is greater than the other as my other hypothesis, this is called a one-tailed test. Okay. I've said all that just to tell you to do one thing the rest of your life. Okay, this has an effect on your significance. Okay, it could get you into trouble. So in other words, in general, just assume you have a two-tailed test. Just always, when in doubt, it's a two-tailed test. It's a very conservative way to deal with things. So if you happen to be putting together a test and you're using a computer program, and the computer program says, yeah, but is this a one-tail or two-tail? Just put 2 and keep right on moving. You're fine with that. No one will get mad. The stats police will not come after you for that. Okay, so here's back to where I left us here. We're going to determine the difference between 2 means. These are our hypotheses. Okay. The procedure is somewhat similar to the F test. Okay. You determine a calculated t-value. Once again. So now what you do is you determine, erase all this. So once again, we're going to come up with a calculated t. Okay, and we're going to compare it to a critical t. Okay, and it's the same rules. Okay, if calculated t is greater than critical t, we have a significant difference in the means. calculated T is less than critical T, no significant difference. We're gonna watch these two steps, so that's kind of universal. Okay. But unlike the t-test, determining the calculated t takes some work. The following thing I'm going to write down is in your hymnal, okay? Do not write this equation down. Or you can if you want. Knock yourself out, but you might have trouble keeping up. Okay, so what the t-value is based on is you subtract one mean from the other mean, take the absolute value. Okay, that's not too hard. And then you divide that by the significant difference multiplied by the variance of one of the means plus the significant difference multiplied by the variance of the other mean. Oh, before you do that though, divide that by the number you have from each sample minus 2. And then take the square root of that. And then take the square, multiply that by the square root of 1 over n times 1 over n to 2. Okay. And then you got it. That's the t-value. So it's a little different. Okay. And it's on page 86 of your handbook. To let you know that equation. Okay. And this is one of those great back in my day moments. It was very, I've taught this course before where students had to calculate t this way. You're not gonna have to. But just, here's what it looks like here, okay? So t-value, and I'm doing the t-value again, once again for mass. So there are the means, minus each other, and I want the absolute value subtracted by standard of the degrees of freedom times the number, divided by the numbers minus 1, take the square root of that, multiply it by 1 minus 43 over 1 minus 39. This is what that looks like if I boil it down. If I boil it down a little farther, it looks like this. And then finally, 4 minus 1 over 188. And then when I'm done, I would come up with 2.171. Lots of time in there to make mistakes. But this is how you would calculate that out. So all I did was boil those numbers down and I came up with 2.171. So my calculated t is 2.171. Okay, now what? Now we got to find the critical t. Okay. Page 90 this time of your handbook. This is the t-value. It's much more easy to look at. T-values are set up by, so this is the t-value set up for alpha value 0.05, which of course that's where we play. So that's what that one looks like here. So they're much easier to use. T-value is, once you've got that crazy number, they're much easier to use. So we calculate the degrees of freedom for this. The degrees of freedom is calculated by adding up each of the ends and subtracting each of the ends by 1, or adding them up and subtracting the total by 2. So we did that before earlier. Okay. So that gives us degrees of freedom are 80. So you look at your table then for it. Is there an 80 on this table for degrees of freedom?
No.
No. What's the next lowest one?
60.
60. Okay. What is the value for 60?
2.
Okay. Look up the closest value for 80. It's 2. Okay. So, calculated t is greater than critical t. So we reject O. What does this mean? Come back and what the heck did we just do? What does this tell us?
There is a significant difference between the two means.
Okay, say it nice and loud, I didn't hear you.
There's a significant difference between the two means.
Okay. In other words, yeah, this is the math. There's some difference between pond A and pond B. The crawfish are heavier in pond B than they are in pond A, significantly heavier. Now you've done something. At an alpha value of 0.05, you found significance. Woohoo! You can publish. This will get you the Nobel Prize, I think, right here. Okay. All right. That is what is called a paired t-test. Excuse me, a two-sample t-test. Okay. I'm going to give you another example of a study here. Okay. I have two shooters here, and they're in what's called a progressive shooting contest. What they're doing is they're shooting at a target and take a shot, then they move to a farther distance, shoot again, take a shot, move farther back again, and do it again. So for example, they're going to shoot at 10 meters, 20 meters, 30 meters, 50 meters, 75 meters, and 100 meters at these two targets. Okay? 0 to 10 scoring on each target. Okay. This is their results. Shooter A's, either shooter A scores, shooter B scores. Okay. Who did better? If you can trust my means.
The shooter A.
Shooter A did better. Sure. Okay. So she's a better shot. Okay. But as statisticians, we want to ask the question. Yes, she's better, but 8.7 versus 9.5, is that a significantly better? Okay. So is the mean 9.5 significantly better than the mean 8.7? What test would you want to use to test the difference between two means?
Two sample test.
You would want to use a t-test, right? Okay. Okay. Assume that these data are normally distributed, okay? Assume also that we ran an f-test and we found there's no significant differences between the variances. Can we use the two-sample t-test?
No.
Why can't we? Well, if yes, so the test that we just ran on the crawfish, can we use that same test?
No.
You're saying no. Why are you saying no?
Because the sets of data aren't really independent from
They're
each
nowhere
other.
near independent, are they? Okay, these guys are tied together because they're the same distance. These guys are tied together. These data are not independent of each other. You cannot use a two-sample t-test. So you can't throw your arms up in the air and start crying. You need to use a different test. Okay. So again, this is the observation that was broken here. This is one here. The observation, one set of data are independent from the other. They're not. They were shot at the same distance. So I can't just mix up the data on one side versus the other side. Okay. So the answer is no to a two-sample t-test. But you're not dead in the water then. Okay. There's also what is known as a paired t-test, which will save if you have paired t-test, there's still a t-test. So what I'm driving at here, in the world there are 3 t-tests that you can run into. The one that we just used on the crawfish data was the two-sample t-test that assumed homoscedasticity. Okay? If the f-test had given us a problem, we would have used a two-sample t-test assuming heteroscedasticity. In this third one here, we've got into a situation where the data are not parametric, but they are paired. We used a paired t-test. You're going to be learning how you can do each and every one of these t-tests, not by, I think that's all I was added here, not by, okay. Yeah, so the good news is, yeah, all of these tests that I've given you here can be easily run on Excel. That's why, in the past, I require people to be able to calculate out a t-statistic by hand. No, Excel, you just put the data in, and Excel will give you a t-value. Okay, it's one of the built-in statistical functions. And the report it gives you is what is called a p-value. Okay. So, just to show you what might happen here, I gotta do it by hand, I guess. No, I don't think I'm gonna bother because you're gonna be doing it in your report because it's gonna. But basically, Excel's gonna ask you. You're gonna type in the function is called equal t-test. So you would type in into some square on the table, you type in equal t-test. You can spell it however you want, doesn't really matter. I mean, capital or lower that. You're gonna put a paren, and then you're gonna have, of course, a line of data here, and a line of data right next to it. So let's say your first set of data, I got square A, 1, 2, 3, 4 on down. B, 1, 2, 3, 4, all up and down. So let's say your data, you have 10 measurements. So your data column A runs from A1 all the way to A10. Your data, we have the same number of measures. They don't have to be equal for this test. So in fact, let's don't make them equal. This one runs from B1 all the way down to B15. Okay. And you're asking, I want to know if the mean of these 10 numbers is significantly different than the mean of these 10 numbers. I need a t-test. So I hit t-test, and Excel will prompt you, give me your first array of data. This is an array. And I'll call it array 1. This is an array. And they'll ask you for array 2. So, array 1 that's A1, A10. And then you put that in, and Excel says, well, give me the other array. Okay, that's B1, B15. Okay, and Excel says, okay, how many tails? How many tails is this?
2.
2. We don't even think about it. 2. Okay. And then Excel asks you, which one of the t-tests do you want to use? Okay. If you type a 1 here, you've told Excel this is a paired t-test. This is not a paired t-test. Okay. If you type a 2 into the spot, you're telling Excel, I want to run a 2 sample t-tests assuming homoscedastic data, which means you would have had to have already run the f-test to know the answer to that. Let's say we did, okay? And then you type in 3, I want to do a 2 sample t-test, but the data are heteroscedastic. So we say we would run here, let's say that we ran the f-test, and the f-test says the variances were significantly different. The data are heteroscedastic, so we'll put a 3. Okay. When you hit return, what will pop up into this square is a number. Okay. And that number might be 0.0348, whatever. It's going to go on and on. We only care about the first 3 digits. Okay. This number is a p-value. So now I'm going to rattle your cage and ask you, do you remember what a p-value tells you? What is a P stands for what word?
Probability.
Probability. Now I'm going to ask you, P stands for probability of what?
Nothing happened.
That the null is true.
Oh, that the null is true. Okay? And we don't want the null to be true. We want that probability to be small. How small?
0.05.
Smaller than 0.05. Okay. Are these two means significantly different?
No.
What's the alpha value? What is the significance level I want to be less than? 0.05.
So yes.
They are significantly different.
Okay, cool.
Yeah, 0.03. Okay. So again, the last thing I want to cover here is kind of a pet peeve of mine. When Excel calculates values for you, okay? And when you put data into Excel, you take the mean, okay? So let's say I took the mean of all these points here, whatever they were, and Excel calculates the mean, and the mean of these numbers happens to be 87.813632841. And I ask you for what's the mean. What are you going to tell me? Are you going to write down it's 87? So basically you were measuring, this is a measurement you were making in inches. and you were using an inch ruler measuring to the nearest inch, okay? So you got an answer 87.8163, whatever, 2 inches. If you put that on a test or a piece of paper, I'm gonna be really angry. I'm gonna ask you, how do you know this wasn't 4.2 instead of 4.1? You know, this is all garbage. Do not report garbage on your papers. Basically, this is about as significant as you could get, right about there. Be realistic when you report your numbers. When you report a p-value, okay? This p-value I probably would have reported there or at the most there. Don't be stretching these things out at a zillion miles. Okay? It's very rookie to be doing that. Because you're acting as like you have your equipment is that accurate that you could take your measurements out to that point. So don't be doing that. I think that's about all I really wanted to scream at you about today. Let me see. Yes.
So are you still going to run a 2-sample t-test if the f-test proved to be heteroscedastic?
Proved to be. If you reject it all, yeah.
Right.
If it shows, yes, you're still going to run a
Okay.
2-sample t-test for heteroscedastic data.
Okay, because I
That's the number
thought,
3. Yeah.
right, because I thought that for the parametric test, one of the criteria was
Right.
that there had to be no
Yes,
sibling.
yes, and this one accounts for that.
Okay.
This one is made up for. Yeah, it's we know you're not parametric.
Okay.
And there's a fudge factor that's been put in. So it's a little harder to hit the p-value this way.
Okay.
Than how it makes up for that. Okay. So you have your assignments, so pretty much everything you'll be doing covers this. You'll be calculating F values, F statistics and T statistics using Excel. Okay? So in